So, okay, hello. Yeah, black screen. Anyways, so please let me know if you can hear me and you're ready to work. Get the template 17.2. So template 17.2 ready for work. So plus minus if there's some problems. And today we'll have really interesting type of models. There's not actually too long distance to state-of-the-art models that they use, for example, for training Dota or like any of those cool models that we have seen in the news. Of course, to actually train that kind of model, that's not an easy task at all. It takes huge resources and also, yeah, and tweaking and searching the parameters. But anyways, today we'll have another approach. So I'm adding that one. Just a second, I'm thinking. Okay, we'll first start by looking at the theory, and I also want just quickly drop in a Mega Drive for some joining without the classroom to get the template. Just a second, we'll do that. Then we'll look at the material, and then we implement a couple of models. I don't think that we'll be able to implement all of the models. You will see that policy gradient methods, and actually a lot of deep learning, reinforcement learning methods, there are so many variations of that, it's like impossible to implement just in this, this tutorial. It probably would be possible to do just the whole course in reinforcement learning. I bet there are already like enrolled some universities or online courses where you can just do like 17 lessons in workshops in reinforcement learning alone, nothing else. So this will be the template. I will need to make sure that my templates, I can have them assigned. Okay, so anyways, let's dig into the model. So this image I like really a lot, but maybe it's not easy to understand immediately. But this kind of helps to represent what reinforcement learning the policy gradient is. So there is a derivation, like you can get from the equations, starting from like a basic reinforce, I think it was called the algorithm, where you can get the approximation of the gradient. So the approximation of the gradient of the model, that is the that you can get from this equation. So logarithm of probability of your policy multiplied by the reward, like cumulative reward at any time step. So we already know how to like calculate cumulative reward, right, with a discount factor. And this is just like a probability. So we don't have any more agent that can we don't have any more agent that can predict what is the value of a particular state. Connection. Did the stream die? I think it did not die, hopefully. Can you still hear me? So now I have really stable, cool connection. I really hope that you are still there. Yeah, whew. Okay, so the YouTube streaming is really great in the sense that even if I lose a connection for a few seconds, I can get back, so that's great. Anyways, sorry for this interruption. Okay, so again, the cumulative reward, that's one we already looked, and here I like this image because what it is, maybe I should make it larger myself. So the idea is that, for example, we have time steps here on the x-axis. Then we have the actions on y-axis. And then we have the rewards on the z-axis. And what this image means is that if we have a model that do not predict the value of the reward of the state, but it just predicts which action should I take. And if we plot the whole trajectory, so the trajectory means just the all of the state changes that we had in the same episode. This line, each of those lines is the episodes, and we want those episodes that produces higher rewards, and we training model so in the manner that it will be penalized when it gives like bad reward trajectories, and it will give loss will be smaller in some sense, because depending on the scaling of the rewards, it can be also negative. So basically for those situations where we are up the hill, and if we are already up the hill and basically we already learned this perfectly, then in that case it might be that the loss would be 0 anyways. So we'll see that in a second, but it's kind of I think cool idea that you could think that for this kind of loss function, you would need to have the whole trajectory. This is not anymore each step, like each transition, right? In this case, we need to know what is the actual error value, what is the actual cumulative reward. So maybe even if we change this z, this is not actually z rewards, it's actually zr, the cumulative value. And yeah, what's written here? Likelihood ratio changes of experience paths, right? That's cool. Okay, so just before we move on, I want to share you also some other picture. So right now we're looking at the policy gradient reinforcement learning, but there exists many kinds of reinforcement learning like methods and the loss functions and all sorts of things. So this is just really a small part of this. There is so much more. So just to give you a brief intro also in this direction, because yesterday we just looked at the Q learning, the DQN and the double DQN, and that was just the the very basics of what it is in general, but there are so many things that we could cover. So for example, this section, all of the models, the ones that we will look today, these are model-free reinforcement learning. So that means that we don't have a simulation of the world. So if we have some kind of simulator for the world, we can do the rollouts, right? We can simulate what will be the reward, and then we can learn in a different way. So that's one way. And then also there is the Q value. So this is choosing the state with the higher potential value. And policy optimization that we'll look today, we look with the policy gradient and the actor critic and trust region policy optimization, maybe PPO, and though that we will be able to do all of this. But anyways, so all of this, it means that we are looking at the policy. So the policy is decision, what we want to do, the action. So the action should be chosen not dependent on the highest value, but kind of the intuition of where we should go in the particular situation with regards to states. And at the end, very end, we will get the best value. It's not like we're trying to predict for every state what will be the best value. We'll just move by intuition and hope that the end will have the best value. And then there are those that are in between. So the DDPG, that's an interesting one because it's kind of copying the gradients from one model to another. That's really not... so there are quite interesting approaches as well. Anyways, we'll look today at these ones. And the first one we'll try to do is the one that you also have in the 17.2 task. So that one is the very basic, one of the most simplest version of the policy gradient model. We will do also other variations. There are really a lot of variations that you can try with policy gradient models. So here the idea is that we would have the discounted the cumulative reward. So the discount factor is just for the importance. So I mean, like, how important is the future reward with regards to current reward? So that's one. Then the loss function itself looks like that. So first of all, we need to know what is the R here for every policy that we can produce. Also, sometimes you write this part as a probability, so maybe you would like to sample some probability from that distribution that you get out of here. So it might be in both ways, because in general the output is already probability distribution. And the one thing that we need to note is that this will be offline learning. So the PG will be offline learning, but the DDQN that we did yesterday is the online learning, because that we can do while we are producing the episodes. But this one we can do only when we have the full episode. If we don't have the full episode, we cannot have this value here. Also, be aware that this kind of loss function, so this is, I think it was called reinforce, very old actually loss function, and is not stable. So you will see that there are like some optimizations that maybe we will manage to do. It's not really hard to do those. So there is one trust region policy optimization and proximal policy optimization. Proximal policy optimization is basically the same as trust region policy optimization with some clipping, with also some theoretical background with that. So, okay, so let's do this one. And we'll also look at some other versions. So, okay, let's go to the code. So where can I share my code? Just a second. Again, warning, I don't know how many of you tried to play with yesterday's code, you know. When you start playing with all of these codes, again, today I already lost a lot of time just like playing around with it. Anyway, because it's like addictive when you start trying to like make it better. Anyways, so here the model is made in a way that you can copy all of this script in Google Colab and run it immediately. So the only thing maybe you need to run this first line, because today when we will try to do these policy gradient, this is super slow. I mean, like with the DDQN, there is a chance of getting some good landings very fast. With this one, it probably needs to be trained like thousands of episodes. But anyways, so the model, first of all, we can use there's another really big advantage why policy gradient is better, because you can also have as an output here, not the softmax, but the, for example, mean and standard deviation, and then you can calculate the normal distribution. And in that way, you can have... Can you still hear me? Yes, the spinning of the wheel. I really hope that you can still hear me. The funny thing is that today, my problem is not actually my internet provider, but the physical internet cable, because I have been like using it for a while, and it seems like that that it's broken. So I really hope that I will not touch my table too often. So I'll try to move very slowly, just not lose connection again, because as soon as it drops, then hopefully I can manage to get it back by twiggling it. Anyway, I need to fix my cable. Anyways, so here, what I was trying to tell you, so maybe I could write in comments as well. So if the output of agent, so let me zoom in, agent should be if the output of agent should be continuous value. Okay, so I have some mistake here. Anyways, you get the point. Continuous value like steering, like for example steering a car, then in that case you should not have softmax here. Do not add softmax, but do what we did with the variational autoencoder, if you remember, but add mu plus and sigma, like in variational autoencoder. And then basically you can get the sample the value for the car steering, for example, and then also you can calculate the probability of getting the like any value, whatever. So, and you can then use that probability in the equation that I just showed you. So this policy gradient is better in that sense as well. So, but we'll still use right now the just the softmax-based probability distribution, this with the discrete values, so that you don't need to spend time on this part. The one thing that I also added here is from yesterday, prioritized replay memory. Again, the one thing normally when you do the policy gradient, you would try to run it through the last episode, with the batches, you know. But I don't like that approach too much because, so personally we will run through the episode because we have every new transition as a maximum step here. But at the same time, I like much better some kind of prioritized replay where we have the loss values as our guiding direction. So that would stabilize the learning. It would make it a little bit faster. I'm not sure how many of these kind of state-of-the-art models focus on this area, but at least for the tutorial purposes, it'd be great that we should not wait like 10,000 episodes before starting to seeing something. So that's why I'm adding some hacks. So the one hack is replay, prioritized replay memory. So then we have a PG agent here, so policy gradient. So the policy is in English means the kind of when you have politicians, right, that makes decisions. So this is our politician, right? So anyway, we have this one. Then we have the same code as yesterday. Then we have the new part here where we need to calculate the new loss function. We also see that we don't need any more all of the other values in our transitions. So we need only the state, we need the action, we need the cumulative reward pre-calculated. So that we will add. And here in the bottom part, the same thing as yesterday, only again, I suggest that you remove this one. So this will never actually happen if we have the this kind of combination that we will render the agent only if we have 10th episode with the 100 score. I'm just like, I will be happy if we get the score over 0, like in maybe in 1,000 epochs or maybe 1,000 episodes or maybe 500 episodes. So we'll do that one. And then we need to, there's another thing. So see, there's a transitions, right? So we are storing the transitions in between each of the steps. And then afterward, we will go through the transitions and calculate and add everything to the replay memory, and then we'll do the replay. So again, we need to do this because we need the real cumulative discounted reward. So if we don't have that value, then we cannot really train it. And the only way how to do that is by having the offline version, right? But after the episode, we need to calculate what was our rewards, and then we need to use them. So let's do the offline version then. So we'll need to do some loops here. So we can do the loop in either way. It can be in a forward manner or reversed manner. So just I will do the forward manner here in range of So let me think. So we need the transition. Okay, let's not do the range, but do the enumerate. And then the transitions. And then there will be the, so the T and transition. So we have this one, and we use this because we need to calculate the large R value, right? So the large R value with regards to every T time step. So beginning it will be 0, and then depending on the, basically depending on the way how we will calculate it. So first of all, we'll go, I think, step by step in the future. So for the future, and the there will be the transition future in enumerate. So from this transition till the future transition, except I would like to have the first one up there, just a second. So there will be, the next one will be T plus 1 till the end. And here we'll also have the, from the RT from this one. So the -1, the last element. In this, we have the RT, but maybe it's not clear. Maybe we should unpack it so to make it clear. So let's make it clear. To unpack it. So the transition unpacked looks like this. And this is the large RT here. Then we can also unpack it, the future transitions here. So this be SF, RF, RF, like that. So those will be the future ones. Then also, oops, we will use only this one if the T is smaller than length of transitions -1. So we have this one, and this part will be inside that condition. By the way, you can also write these things in this way. This is also a fun way to write it in the Python, but let's don't make it too difficult. So we have this structure. Now we need to add the RT values step by step. So RT plus, yep, so the gamma, args. So the only problem, okay, no, but from the T it will be fine. So args gamma, like it is powered of TF, so that is our time step with regards to current time step in the future, multiplied by RF here. And also we can, to clear the code a little bit, we can make these things as these underlines. That is a common way in the Python, as people are like writing the variables that they don't need actually, but they exist there. So this will be like that. So we have the RT calculated with regards to every time step here. So that's fine. Then we need to update it. So to update it properly, we can use the translation -1. So that is the last element, the RT there, the last element. Or we could also use these variables and construct a new transition, but I just want to update it. By the way, I don't like it because now then it can affect the next result. So let's make it new one. So ST AT here, and let's then use the new one. Sorry for this. So agent will learn something in the replay memory. So replay memory, push, and the new transition will be ST, AT with the large RT. Hopefully this code works. I will not run it yet because the loss function is missing. So I will copy this part inside the Jamboard, and then we will see if we can get it working, then update other things. So the Jamboard slide number 4. So this is the calculation of the trajectory. As I say, normally people do this by just going through all of the trajectory and updating the gradients and then training the model. But maybe that's not also too bad idea in the sense that we could do something with priority. So just a second. So we could do following. We could add additional extra loop for training. So for in, I will need to update then the Jamboard again. For in range integer. So not in, yeah, integer sale or mat sale. I hope we don't have so the NP sale then. Hopefully it will work. So what I want to calculate here is to how many times we should repeat this. So len transitions divided by batch size. So at least this amount, but maybe more. So what I then propose is to maybe multiply this by some 1.5. So this is just, you can actually write hard code like repeat 10 times or whatever, but I'm just making a little bit more interesting way how to estimate how many times should we repeat the training process here. And there's another not nice thing now here, so, but you can leave it as it is. So the one thing that optionally you can add is to have the E loss S. So the episode losses that we can have append loss, and then all losses can be mean of this, NP mean. But this is optional. So I mean, the loss part and also actually all of this bottom part of the code, this is not something that you definitely need to do. So if you want to make it a little bit better, so again, a lot of things that you can invent or hack or think about. So anyways, hopefully this code also will work. If something of that will not work, I will need to update the Jamboard. So then the training procedure. So the training procedure should be quite straightforward, hopefully simple enough. There are multiple ways actually how to do this. So there is a sampling method and then there is a direct method. So we can let's start by direct method and then see what are the results, and then we can do the sampling method as well. So direct method would be following. So loss would be the minus RC. By the way, maybe on the slides there was not minus in the front because maybe that was a maximization problem. And if we have something as a maximization, if we add minus, then we can minimize things. So the PyTorch optimizers usually minimize things. So torch logarithm of now, we should select the action. We actually should run it. So A, all. So these will be all options for the particular state. So, whoops, self model, forward the state, and then we will select only the one option that we actually want to choose. based on what we chose in the actual model. So indexes, comma, 18, 0. So that would be enough. And then AT here, so these will be the probabilities, plus some kind of safety against the zero logarithm. Also, so the probabilities will also always be positive from 0 to 1, but 0 we don't want, so that's fine. Okay, hopefully this part of the code works. I need to check it. So if I run it, what happens? If it will work, I will drop this in the Jamboard. By the way, if you have any questions regards to what we already did, or the loss functions, or the logic, please let me know. So we'll see. I also made the way that the agent is like the plot is only updated once in 100 steps for the Jamboard. So right now I think this is an exploration phase because the epsilon is quite large. So this is definitely exploration phase. But at least the code works, so let me quickly drop the code and onto the Jamboard, and then I will run it actually on the Google Colab and see if it works properly. What I see in my local experiment, that it starts learning to have longer episodes, so that's I think is good sign. So I'm dropping this also to the Jamboard. So before moving onwards, I want you to make this model for yourself. You can like adjust it as you want. There's a lot of opportunities to play around. And yeah, and meanwhile, I will be running this code on the Jamboard. I mean in the Google Colab. I don't know why I always like those two words in my brain are too similar. I don't know why, because I use them a lot. So we have the code here on the slide number 4 for the equation of the slide number 3. And in the Jamboard, okay, I'm not a robot. Okay, so this is not cool. Okay, okay, so I need to open a new collab, right? This one is hanged up, so new, no collab. And that's an opportunity to show you how to run this on Google Colab. So first I will have 2 cells. So first cell, second cell, I copy my code here. And I want in my first cell to install with the exclamation mark, I can install things inside so this is a command line basically inside the virtual machine. So then change runtime to GPU. I need to reload it. Hopefully it will not lose something. Okay, that's fine. It's not the private outputs, okay, like that. So then I run this one. Too many sessions. This is not true. I don't have too many sessions. All of my sessions are closed. It just hanged up. Hopefully I can manage to get the GPU somehow. Oh no. So manage sessions, terminate. I guess you can have only one session on Google Colab, I guess, for the GPU. So now I'm running the first line. Okay, installs the box 2D. Then I'm running the second line, all of my code here. So we have the replay memory of 5,000 like frames, or the transitions. We have the gamma of 0.9. Maybe it could be lower. We have the hidden size. We have some stuff. The model itself also really simple. So this could be leaky rel as well. It doesn't, I don't know, I just used the one that we used for the transformer. So then now it trains much faster, and hopefully we will see something, at least something in a positive direction. So the episodes gets a little bit longer, the loss gets a little bit lower, the score is still fluctuating really, so the score actually gets lower, so that's not cool. Okay, so while it's training and while you are finishing up the code, I will look at my code to see if I don't have any bugs here. I think I found already one bug. Okay, that's not a huge bug, I think, in general, but I will update also the Jamboard. So here the TF, it starts from 0, but this is not the case actually what we need here. So either you could have here T plus 1 like that, or we can rewrite it a little bit. So that was the one thing that I was wondering about. So here we can have R as 0, and this could start from just T, and then it would be fine. Because otherwise the equation is not correct, because the next step would not be then gamma, that would be gamma 1 as well. So I mean gamma 0.9. So there's a very small change, but I don't think that change would give a huge benefit, but still that would be more correct to make it like this way. So I will update the Jamboard. Okay, and we'll try to run it again on the Google Colab using this code. You can try on Google Colab as well. Hopefully it will not get banned by using the same code many times in the Google Colab. So I'm running this. We'll see if it works. Anyways, so while we wait some results, fine-tune it, maybe you can find some good parameters and share to others. So while we do that part, please let me know. Okay, what is this? My rainbow cursor. Anyway, so while we wait for the results, let me know if you get first of all, if you finish the code. So is 17.2 done? So if there is some problems, please let me know in the chat. If it's done, let me know. Meanwhile, I will prepare the next task, and we'll see what happens with the training. So my training results look something like this. They're actually not too good. We will add also maybe some other change here. Okay, I have idea what to do as well. Yeah, let's add some stabilizing factor here. So there could be a lot of ways how to stabilize it, but anyways, if you have the basic code ready, then let me know. But I want to add another stabilizing factor here. So one that we can add is following. So in the replay memory, when I add the samples, I also store the RS values. So these will be the actual cumulative rewards. So we can use those values to a little bit scale the R here. So to scale this value, we could use we can standardize it basically. So to do that, we could do RC minus MP mean of what we have inside our memory. So self replay memory, or C, there should be those, I think, hopefully. Let me check. Yes, there is that. So the standardization, right? We did the standardization for a lot of data sets in past. So this one and the STD. Because this loss function is not very stable, it would be great that at least there is some kind of normalization there. Okay, so I'm not sure, hopefully everything works. If it works, I will update also the Jamboard. And hopefully this will produce a little bit better results. Okay, this function works, so I will update the Jamboard. Again, you probably, if you're smart enough, you can think also another ways how to normalize the R cumulative values. For example, you could have them always being from 0 to infinity, for example. That might help some things for the loss function, maybe. So, or also when you store it, you could track what is all of the previous R values have ever seen. So, okay, my computer is really slow right now. Okay, cannot get this a little bit bigger. Okay, good. Hopefully you can see it. So I updated a little bit the normalization of the R value. Okay, so this should be fine. And we can move this a little bit on this side. Okay. So, and okay, I will share the Jamboard. So I added in the Jamboard, updated these codes, and if you look at the tables here on the plots, so now it is a little bit better. So the score is still fluctuating quite a lot. The loss is also not very stable, but the episode seems to become more and more. So, I mean, the episodes gets a little bit longer. Hopefully that's a good sign. But yes, it's not perfect at all. As I say, with the policy gradient alone, it's not easy to train it. But anyways, okay. So while this is running, I will prepare the next task. So let me think, what will be the next one? Next one we could do, probably we could do the actor critic. That would probably be a good thing to try out. So I'm just thinking, yeah, I will give a template, otherwise it will be too long. Yeah, so let me know in the chat when you're done with this one. And meanwhile, I will prepare the actor critic template that we will use for the next task. C1 plus, that's great, 2 pluses. Not great results, that's true. With just pure policy gradient, I would give a best shot if we add the trusted region policy optimization. Maybe we should do that. Okay, maybe before doing the next task, probably I will show you how to also do some kind of normalization with this trust region policy optimization, and it's very it's not very far from PPO. That is kind of state-of-the-art approach. But of course, you would also need the full actor critic, but we will do that as well. So just a second. I just realized that my template didn't have the priority replay as in the first template. So I need to quickly update it a little bit. Okay, I can do this. Anyways, okay, probably I should do this step by step. Anyways, no, I will prepare a template. Otherwise, it will be too long for you to catch up with the template. So what I'm going to do, I will copy some parts of what we just did in our current template to the new one, because I don't want to make it too different from the current one. It will not be long. Just a second, so you have time to catch up. Try out some other parameters. Try on the Google Colab. Oh, by the way, did we update the priorities? Yes, we did. Whew. I'm a little bit scared. Maybe we forgot about that. Okay, so that's good. It's very easy to forget some small nuance here, and then nothing works as we expected. Very soon I will be ready to do this. Okay, I hope my template is ready, but before the new task that we'll do together, before that one, I still want to do something with you with the previous task. So I will see what I got here from this experiment. We got nothing great. Like, it's actually a little bit lower than expected. So the random stuff worked a little bit better. So the one thing, episodes is longer. So maybe we need the gamma lower. So the episodes are longer. So that's much better than random. But the scores are not better. But anyways, let's do some small update here. So one thing that we could add is the same way as with the DQN when we had double DQN, right, where there was a target model. So there is a trusted region policy optimization. And that idea is also a little bit similar to the like DDQN. Like DDQN, where the idea is that we have some locked target model. So there is a target model, target policy model for stabilization. And the way how it works, I probably need to pull up LaTeX. It's so it's updated with some time, like the interval, or also could be updated with some kind of algorithm, right? So math call. So maybe I can try to show you how I write it. Whoops, not like that. So math call L will be the. So it will be the frac of, okay, it will be, first of all, it will be minus R T C dot, or doesn't matter, it just can be this one. And then frac of the logarithm of the policy, of the probability for the policy. So P of the state, and yeah, for the state and the action, basically what is the probability. So STAT, and divided by the same model that we got some few episodes before, or few like, let's say 10,000 frames before. So there will be the target model as well, and this will be just the policy model, P. So the policy in the like in the reinforcement learning, that's always a P. So there will be a target and this one, and also we could simplify it, or sorry, maybe that's a logarithm over, just over. I will double check. What was the equation actually? Maybe I should pull up the paper. TRPO, Trusted Region Policy Optimization. Oh, maybe I can even show you how to do that. So there in archive you can get all those papers. I think yesterday we also looked at one of the papers. First of all, they use the actor critic that we will code in just in a second, but just for the policy part, we can also use this one. So where is the policy part? Policy part. Oh, here. So this is the policy, and also to the old Q or A. Okay. Yes, so I have a small mistake here. So it must be logarithm in front. So it should be like that. And then we can, of course, simplify it by having the logarithms as subtracted to each other. So that's one thing we could do as well. Or we could leave it as that. So anyways, there is the option to subtract them as well, because that's a logarithmic property. So anyways, I don't want to just spend too much time on this. Okay, we'll do a small experiment on this and then move to the actor critic. Maybe I should not start doing this, but anyways, I was just wanted to show you. So there are some methods to stabilize the kind of the policy model. Copy method. Okay, let's see. Add it here. We'll try to do this in the code now. To do this in this code of the policy gradient method, of course, the one thing is maybe you could just skip this part if you're not interested, but if you are interested, you can try to do this yourself as well. So this is the same idea as we had before with those state dictionary copying, right, for the double DQN. So there is just another model here, T model. Then we also need to have, so this is not really a requirement for this task. It's just something that I want to try out. And if somebody is interested in this, definitely can also try this out. So then there was the function from yesterday. I just want to copy it because otherwise it will take too much time, or maybe I should write it if somebody is following. So anyway, def update target model. This is the function from yesterday. So self T model should be updated from load state dictionary from self P model and the state dictionary. And we will copy the values in very beginning of the self copying values, and also we will copy these. Okay, I will add this also to the Jamboard. This is one stabilization trick that could be used. Okay, so the Jamboard. But of this like if you want a proper implementation as in the paper, then you need to do the actor critic as well. So this is just one part of the whole model. These reinforcement learning models can be really complicated with a lot of paths. So here this will be this one, right? Then we need to update it by some target frames. Do we have target frames parameter? We don't have the parameter. So we can add some parameter, target update. So we can update it maybe once in, let's say, 2000 episodes, 2000 frames, or maybe let's say 3000 frames, whatever. Really don't know the hyperparameters right now, unfortunately. So then the frame 0 here, and then we add some frames here. So we could do that actually down here. So the frames plus len of transitions, and if frames are larger than args dot target update, then we do the the agent update target model, and frames should be 0. So because this is offline, we don't train something online. That's why maybe this would be a good idea. And also this should be done after the replay here. So I will copy these lines also to the Jamboard. Then the last part is only in the actual training procedure here. Some things also can be improved here. Okay, so let's improve even two things here. So first of all, we could use the distribution here. So to do basically the same idea as in the reparentization trick. So we have a prior distribution of A all here. So what we can do is to do the distribution here, and there is torch and then distribute. Well, there is no distribution. Why don't I have it? Torch distribution. So these three. Okay, it's not showing up. Anyway, so torch distributions. Okay, it should be imported, I guess. So you can import up here, import torch distributions, and then you should have it here. So this will be the distribution. And there's a lot of interesting distributions: gamma, beta, Gaussian, all the normal distribution, uniform, right? And there is this categorical distribution as well. So I think that is just a normal distribution. And here we can use these priors of that distribution. And then we can sample this one from dist. Okay, we can either sample and then add the logarithm, or it already have the logarithm here. So this will be then AT0. So the logarithm already added. So that's good. If the logarithm is already added, then that's not cool actually. Okay, so sample. Then we would need to have like a little bit different equation, but still it's possible. So this is a sample shape, sorry, log probability. This is a value of that probability. Just a second, we can try to do this in a different way. So if I sample it from that probability, then I just need to again select it. Okay, well, I will change a little bit the equation, otherwise I just need two other lines and I don't want to have it. So anyway, this one, then maybe I carried away a little bit, made it too complicated already. So then there is a target model. Again, the same thing happening as this one. The only difference here should be that this variable, so this will be so this will be, let's say, TAT, or now it's not understandable. So a target and a T. And here we need to have detached then, detached, because we don't want to train the actual model of this one. Or maybe we could detach also here, so it doesn't matter actually where we can detach it. Okay, so that's great. We have this one. Then we can try to divide both of them. We also need to do the division with the smooth division, because otherwise, if we don't do that, then it can have an error, because it can be division by 0 or logarithm by 0. So that's why we need to do it in this way. I really hope that everything is fine now, but there is some red lines. Why there is red lines? RC missing. How can it be? It's not missing. Okay, this one is fine. This one is fine. So there is an additional. Okay. Yeah, that's cool. Okay. So I was thinking that it will take a little bit less time, but again, also these distribution parts are also a little bit optional. So let's see if it works. At least in general, it seems like that it's working. I'm not sure if it's giving great results, but at least it's working. So I will drop this also to the Jamboard and run in the Google Colab, and then let you know if it actually gets some decent results. If not, then the experiment is a little bit failed, but at least you already that you know a new way how to normalize it a little bit. So if you read the paper on trust region policy optimization and then proximal policy optimization, that's a very interesting path for research. There's still, I think, quite a few things that you can discover. So okay, I will share the Jamboard and introduce the next task. I think that's going to be the last task for today because it will also not be very quick. So where is this one? Jamboard. Okay. Great. So the next one in our list, basically to get up till the next one, before that one, I just want to share you another very nice image. So there are already, just with the policy optimization alone, not talking about the actor critic, there is like quite a few ways how you can do this. Actually, they say that all of these are actor critics, but in general, the kind of this part of the multiplications here, the GT is what it means is actually RT. I don't know why they used the GT. So, but the idea is that you can have a lot of things here. So you can, one of these things you already immediately see. So the Q value, right? So you can build your Q actor critic model, replace the RT part here with the Q model, and then you have two parts of the loss function and two-part model, and that's your first actor critic here. But there is also the like advantage version, there is also TD version, and there's quite a few other versions already. So if you think about, let's say, the second one, or the next one as well, basically that's very similar to the second one, is that you would have a situation where you have kind of the decision maker, the politician, right, the policy model, and then you have also the critic. So the critic do not work at all. So the critic is just sitting and criticizing everybody. So it's like in the politics, right? The politicians try to do something, hopefully, and then some others just criticize them. So there is the critic here, and then there is the actor. So the actor is the policy model, and the critic is here. And the critic is observing the way how the politician, the actor, is interacting with the environment, seeing what are the rewards, and then giving error to the policy model. And the way how it does it, like in this case, this is a value function. If this is a value function, then that is the case most likely of the advantage model. This could be also a Q function. If that is a Q function, then that is the second one. So we will build this kind of model, and the equation for this model will be following. So I will pull up the equation. Okay, probably we will skip one part of the equation, the entropy part. So the H is usually called as an entropy, so that is kind of discovery factor. Because we already have the epsilon greedy discovery factor, we could maybe leave out that one. But as you see, this part is the same as before. And the new thing is the advantage function. The advantage function idea is that you would have some kind of model V that is not a Q model, that is a value model. So what it means, it predicts what is the baseline of the values that you can get from, depending on this state, or in this case, the next state. So the idea is that, so here you have for the current state. So for this state, what is the baseline value that you can get, like in average, if you occur in this state, right? So if the spaceship is close to the flags, that is a good average value with regards to any state. So if you are very far away from the flags, that is not probably a good place to be. And yeah, so that is one loss function here. So here the advantage is also used for the loss function. So if you look at these equations, the A is directly put in here as well. And but we also need to know, we need to know all of the RTs. We need to know the whole trajectory, and we also need to predict the next value of this one. And then we use the gamma, and then we subtract it here. So, and then we multiply it here and calculate the actual policy loss. Okay, so hopefully that's clear. If you have some questions specifically to what's not clear here, then please write in the chat. Meanwhile, I will prepare the assignment 17.3. 17.3, implement a advantage actor critic model, and I will add the template. All of this area of working with the deep reinforcement learning, especially with these very complex models, like, because there is such a huge complexity, I mean, like, that means that there's a huge opportunity for a lot of research, you know, like you can change so many moving parts here, and if you change just one of those moving parts, there's opportunity for doing research work and publish some scientific work. So anyway, here is the 17.3 template ready for work. So plus minus if some problems. I will get my template also ready. And meanwhile, I forgot, I guess, to run my code on the Google Colab. Not sure which one was this one that was running. I will check in a second. Okay, this one is a slightly worse performance over time. And this one is not the new model. So I will add the new model. Maybe I can play around with smaller learning rate, I don't know. So if I run it again, yes, it starts training, we'll see what happens. So I see one plus that one person is ready to work. So this one is running, we'll see what we'll get there over time. Hopefully, now it's quite really random because it's still epsilon of 60%. Anyway. Oh, nice. Thank you, Gintz. You're saying that gamma 0.7 helps. That is valuable information. Because, you know, like, properly to do this research, you should do the grid search. You should try out all of the combinations of everything. That's not easy task. So anyway, so I added a little bit smaller gamma, so we'll see what happens. Anyway, let's go back to the code. Where is my code switcher? I see people are ready to work. So actor critic, advantage version. I hope I will not mess it up. So, okay, I have the template here. So the one thing that's already that we will have here is that we have a value function. So up here we have model actor and model critic. The model critic, if you see here at the end, it produces only one scalar output. So this one scalar output is the average or the baseline value based on state alone. So that's one thing here. The model actor is the same as the policy model before. Then we have the prioritized memory. Then we have A2C agent. There is also A3C agent. The A3C agent usually means that this is parallelized on multiple like GPUs and multiple nodes and stuff. So usually, because all of this is so slow, you try to run a lot of episodes in parallel. So A and C, so that actor and critic. So I joined them together with the one trainer, with the one optimizing algorithm. You can also have multiple optimizing algorithms for each of the models. Then the replay part, we will add the loss function here just in a minute, but let's start by this bottom part of adding the episodes, because the adding the episodes to the replay memory again will be different from the previous model, because now the R values are not calculated by cumulative value but using the advantages. So the R's here will not actually be the stored in the memory as the real R's. Those will be actually advantage values. Maybe we should rename them later as well, but anyways. So let's then do this. So so let's see, so for T transition in, so that part you can copy probably, this first line. So transitions, then here we have the let's unpack them. I don't want the risk of copying something as a pointer, so I will better unpack everything. So as like that. This time maybe I can unpack using this syntax just to show you that this is possible. So that's great. Then let's see. So the real RT value in case if the T length, so if we are not at the end of the episode, transitions -1, if you are not at the end of the episode, we want to use that value. Again, this code that you will see is highly unoptimized. So the correct way would be do the batching and all sorts of things. But if we start doing the batching here, the code will be completely unreadable and you will not understand what's happening. So so this will not be optimized. Sorry for that, but that's better than just writing something that's not readable. So let's see. So we'll need to have unpack these things. So ST1, we need this one. We don't need this one. We don't need this one. And then we will unpack all of this from the next time step, T+1. So we're unpacking from this one. And now we need to predict the value, right? So as you see, during the running of the agent, we don't use the value. The critic comes only after the fact of what's happened. So the critics usually criticize after everything already done. So torch float tensor. I hope I write it correctly. So the float tensors should be processed. So let me think. So this is ST. ST is just one transition. And if I want to pass it to the model, I need to run it in this way with the extra array dimension, like that. Then we need to move it to args device. And then we need sorry, there is a problems here. First of all, okay, I will split it out, otherwise it's not readable anymore. I'm starting to writing spaghetti code. So to avoid spaghetti code, let's use, this is a new line, to args device, and here st1, so we are predicting the value for the next step. Then I want to squeeze it back, squeeze. So I'm with a squeeze, I'm like destroying the extra dimension that I created with those squared brackets. So then CPU, then to item, right? So the item would just produce then the scalar value here. So these lines are just needed for the PyTorch to work. So then RT would be plus. We'll also need to check the equation on the Jamboard. The equation, we need to value. Yes, so this will be the, actually this will be the delta value, TD value. So I accidentally said the wrong word. So the RT will be actually the TD value. So let's see. So this will be then the args gamma multiplied by value T. And the new value in RT will be the TD version. So TD gamma. So this is, I mean delta, sorry. So this new RT is this one. By the way, the RT should be also here, like that. Okay, great. So that's great. And now we need to add all of this stuff to the agent. Agent, replay memory, push, the state, all of these things. Now with the new RT value. So for the last state, we didn't change anything. For the last state, we have the same RT as it had. But the previous states we changed. So I really hope that this code works. Maybe I will add a breakpoint and check if it works so far. And if it does, then we will do the loss function part, and then we'll be done with this one, hopefully. Okay, it works. I'm not sure it works correctly, but it works. So anyway, it should be correct, hopefully. So then if I copy this one and drop it on the slide number 8, I will also take a look on my previous experiment in Google Colab. Okay, how can I scroll it? Okay, the previous experiment was not too bad, actually. So it was not definitely perfect, but it's not also it's at least better than before. So what you see, that agent first learned to float in the air forever, or basically for a long time, and then afterwards the agent started to getting at least the average above or zero or above zero or something around that direction. So if you look at the values, let's see what we have here. So that was the one with this trusted region policy optimization type of thing. Okay, the values are not great actually. There are some, hopefully, that are above zero, but again, something not so good happened. Anyways, let's do the actor critic. Hopefully that will work better. Okay, so I added that to the Jamboard. Let's do then the loss function now. So the loss function is here. Again, there is a potential to convert this code into proper trust region policy optimization with the paper that I showed you before, but you just need to, you will need to add the other model here. But we will not do this right now together because of the time constraints as well. So let's see. So here we'll have the very simple stuff actually. So value T will be self model C forward. Okay, this is already with the batch size S T0. And let's squeeze the values, squeeze. And then we have the advantage. So the advantage is the RC. So maybe I will rewrite it. So this is actually delta. So the TD delta, TD delta. In this case, this is a TD delta. So TD delta minus value T. We have the A. Then the next part of that, okay, there is also a problem, or C, TD delta. will be with the sampling. What we did before, let's do the same thing again. So all actions at the state of the t0, so self a model forward state of t0, and then distribution of that that probability distribution that we get for those actions. That will be our prior. So a all, and then we can have the loss function actually. So here will be the loss function will be two parts actually. Okay, so let's do the two parts. So first of all, there will be the minus a detach. So I don't want gradient to go through this part, multiplied by the distribution of log probability. By the way, you can do that also by sampling and then selecting the action and then applying the log. So what is the log probability? What this function does is it does the following. It does the dist sample, then it selects. I just don't want to write those extra lines, and it will just make you confused. So there will be the IDXS, A's. So then we would select from the sample these ones, and also then add the logarithm. So this is what it does. Anyway, so we'll do this one, log probabilities with regards to, not with regards, but using the A's from this. So that's good. Then the last part is that we will need to calculate the loss function of the advantage. So there we could use, let's see, we actually could use the for the advantage. Yeah, we just need to use a actually itself. So a squared. It's really simple. A squared. Okay, we have these things, and hopefully that's about it. I will see if it works. By the way, the Q value, like actor critic, probably takes a lot more code. You would need to have much more code there, probably. So at least the code seems working, but not sure about the results yet. Let's see. Also, did I change the gamma? No, I did not change the gamma. First of all, I will drop this to the Jamboard. Then I will run it again and play around with it a little bit. So, where is the loss function? It is here. At least now, probably at the end of this course, you see that at least you have the glimpse and understanding how to implement all sorts of functions in PyTorch, and then you're like quite well prepared for just taking papers from like latest publications in deep learning and try to implement them and see what are the results, get the state-of-the-art results, hopefully with a lot of training and hyperparameter tuning. But so at least that part, also in the reinforcement learning where it's complex. Okay, I added that to the Jamboard. So I want to have gamma 0.7. Then what we could else play around. So maybe the model. So I will just play around with the model. So this is definitely not very scientific. So if I add extra layer with the leaky relu, and there is a hidden size like that. So I will do the same also for this one. What else could I do? So hidden size, I think it should be smaller. So 32, E minus 4, the batch size quite large, the episodes, the buffer size I think should be enough, 5,000. This one, maybe this is too much, so 3,000. Okay, so I will run it. Interesting, what you mean by spiking at 4,000, so I will see. So I will add this to the Jamboard as well, and to the, not the Jamboard, but to the Google Colab. By the way, if some of you can find parameters that work really good, then please share them. But like that would be like crowdsourcing of parameters, not the grid search, you know. So, anyways, also would be great to add the trust region policy optimization method of like dividing with the fixed target, but don't have time for that as well right now. We'll see what happens. So the loss is growing. That is interesting. But maybe I have some bug. Maybe we can give the priorities for the prioritized memory, not based on both of those values. Okay, so it says that it slowly declines later. Maybe. So, okay, I can do some other hacking here. At least to give you hints how to do this. So the one thing that we could do as well, so first of all, I will move it back a little bit higher learning rate. But so the correlation with learning rate and batch size is the following. So if you have larger batch size, you can have larger learning rate. If you have smaller batch size, you should have a smaller learning rate. So if, for example, the idea is that if your batch size, this is true also for the classification tasks. If you have like batch size of 16, then probably you need E minus 4, E minus 5 or something. If you have batch size of, let's say, 1024, then you could maybe stick with E minus 2 or something. So that's just one small information useful. Then here in this part, I just want to make maybe that update not on the loss. I don't want to update on the loss. Maybe I want to update on the A's itself. So I could try with this one. And maybe we could also, so the squareds are actually quite sensitive to any change. So I don't like actually squared. So let's try to use not squares, but torch ABS, so absolute values. So those are less sensitive to the outliners, and the reinforcement learning is full of outliners. Okay, so we can do that one. Okay, I will try to run this on the Google Colab, see if it works a little bit better, but I cannot guarantee. Yeah, this happens to me as well. Like at like about so I will show you. So about starting 1,000 epochs, 1,000 episodes or so, the loss starts decreasing and the episode length starts increasing. So that's a good sign actually. Okay, so I need to stop it. Sorry for scrolling around. I copied it, running the latest changes. We'll see what happens. Again, quite addictive stuff. You can like change the parameters whole day. So again, the best way would do the grid searches, not by hand. To do the grid searches, just also to feel valuable information. So you can have some kind of other script that generates a lot of parameters, because you know the script right now can be launched with the arguments on the console, right? So if you have some script that generates all sorts of combinations, the full factorial, then you can like easily research everything and better store the values in some like spreadsheet or CSV. So, or the TensorBoard, sorry. Let's see, can we get something better? So the episodes get longer. That's a good sign that episodes get longer. By the way, if episodes get to those 500 limits, then the training will be a lot slower. Interesting that for this particular game, it seemed like the DDQN yesterday gave a little bit better results sooner. But the actor critic also contains some part of the value type of function. So we'll see. Meanwhile, I will think what else we can change to improve. Of course, one is to have the target model. Well, the interesting situation here is the kind of score went down and then up. I've configured it a little bit different parameters. We'll try locally as well while I'm waiting for the Jamboard. Hopefully I will not get anything cool immediately. Most likely. Still the epsilon at 40%. Yeah, the one difference in the epsilon greedy method maybe is also not great. So in the slides I gave you the entropy method. So the entropy method is kind of saying that with some kind of coefficient, you want to make sure that the outputs are not very confident. So if your outputs say that I want 100% go in that direction, so you say probably better don't go in that direction, so with some coefficient. So that was the idea. Okay, funny that the agent now learned to hover. Nice, it landed. Also kind of interesting that the environment do not give that, like the cumulative reward is not that great here. We cannot see actually that the cumulative reward is that great because of the minuses of the hovering. So it's actually landing quite nicely now. Sometimes. At 400 episodes. Well, the last thing today maybe I could do is maybe we should try to change the score. So the score would give us not the cumulative reward, but if it actually landed at the end or not landed at the end. Because it seems like that the agent sometimes lands quite nicely here. And also the scale here is not really cool, because if we get some really high minus values, we don't feel that the agent is getting into positive values. So now it's hovering nicely above here. Okay, it's actually not bad. I got in the row, all of the values are positive in the row, like 5 values positive. So these parameters not too bad. Okay, great. Again, I get like about 3 or 4 values positive in a row. So that's a good note to end this session, that we get an agent that learns how to fly the spaceship on the moon. So, but yeah, see, like I get like huge number of values positive, but the cumulative reward on the chart is not really that great. Cannot see the effect that nicely. Why don't I see it? I get all of the values are positive. I will see them only after 100 epochs. So I guess I found my agent like was working now, but the problem is that the charts will be updated only in 100 epochs. And now I get all of the, so everything is positive right now. I will give you the hyperparameters so you can get your happy agents as well. So I got lucky of striking some good hyperparameters here. Everything is positive, it's few negatives, but like huge number of positives here, and only on 500 epochs, so that's excellent. So let me give you the parameters. So with these parameters, you can get happy agent. I will drop them on the slide 9. So that's a good note to end this course. Happy for that. So, okay, there should be also the plot now. Where is my plot? I want to see my plot. Yeah, see, there's a jump here. We got the positive values, and then agent probably forgot something, but no, it seems good as well. So we got here a jump over 0. See, it's quite significant jump here. So I will copy this one as well. So we see here there is the nice jump. You can also improve probably the way how this is displayed. So it should not be displayed in the way how it's displayed right now, by using the cumulative value if you want to see nicer graphs, but maybe just the terminal value, maybe that will be nicer. So then I will also copy the model architectures, because I also, if you remember, I changed it a little bit. So the model architectures, the actor looks like this. And the critic looks like this. And then the loss function, remember, I also changed from mean square error to mean absolute error because that's a little bit robust to the outliners. So that's another change I did. Probably the same changes you could apply for the previous model and get some better results there as well. So here, the loss function, yeah, and I also update the priority memory based on the advantage values, not based on other values. Cancel here. So the loss function as well. So you have everything here to make your agent happy. And hopefully, also another nice thing that should be added is to save the agent when it's learned the best policy. For example, when we were up to here, I should save the model there and not leave it so that so it forgets something good and then we save something not so good. So anyways, there are some strategies that you can use. For example, saving it at some good checkpoint, then keeping in training, and if it gets worse, then restore to the previous point, then repeat it again and get it better, so you don't go in wrong direction. So, but that's purely a programmatic task. That's not a deep learning task, but that should help. So, and you see that agent right now is doing a lot better, and you see the loss function, even though it's very noisy, but it's reducing. So I think that's it for today. That's also the last session for this course. And hopefully, at least this is fun, because I'm very happy that at the end of the course we get the lander landing on the moon using this actor critic, and the coursework should be submitted by till the end of the May to get. You should get above 40% to get past this course. If you want to keep working with research with me, please let me know on the email and also in the chat. So, and hopefully those of you who get high marks in this course are interested enough to keep researching deep learning and these machine learning models. We have opportunities with a lot of interesting research, so let me know. So that's it for today. Hopefully it's fun. I will add a small homework as well. Try to not make it too difficult. And so it's really fun, I think, to play around with these kind of games. So that's it for today. I will end by showing my spaceship hovering around and slowly landing. Okay, so that's fun task for today. Okay, thank you for